Swayam Prabha. Digital India. Educated India.
So, continuing from the previous lecture on kinetics of bi-substrate enzyme catalyzed reactions, we will be talking about the application of King-Altman method to derive rate expression for some of the complex enzyme reaction mechanisms that we often encounter in the bi-substrate reactions. The second thing, then we will follow up after getting the rate expression for those different mechanisms of the bi-substrate enzyme catalyzed reactions. We will also look into what are the procedures by which one can discriminate between different mechanisms. That means, for a particular enzyme catalyzed reaction, how to identify that which reaction mechanism it follows. So, the general principles about that we will be following. So, coming first to the application of King-Altman method, I will try to illustrate it with a simple intermediate reaction sequence, although it is not a bi-substrate, but a single substrate, but just to illustrate the point so that the system does not become complex immediately, you will be able to appreciate. Let us assume the reaction follows the type of mechanism as indicated here, ES going to ET, then it is a totally reversible reaction, and you have the rate constant K1, K minus 1, K2, K minus 2, K3, K minus 3. Now, as I mentioned that the first step in any reaction mechanism would be to express the mechanism in a cyclic form, so that you can have each of the enzyme species that are present. Here, as you see, there are 3 enzyme species, E, ES and ET. They must form the vertices of the polygon that represents the reaction mechanism. So, you can just write E, of course, it will form a triangle, and E to ES, ES to ET, and then ET to your E, and also show the interaction between the 3 between the enzyme species that are present. Also mention the rate constant in the form of kappa values. That means, the kappa value for E to ES will be K1 into S, and this will be K minus 1, and you will notice that wherever a substrate or product species involved, we will multiply the rate constant with that factor. If there is no substrate or product, then the rate constant will be as it is, and similarly in the case of ES, it will be K2, K minus 2, here you will have K3 and K minus 3 into P. So, now with this information that is available from the reaction mechanism, then we will try to find out the fraction of each of the enzyme species of the total enzyme concentration in the form of the rate constant and the total enzyme concentration. So, essentially, if you consider the first enzyme species, let us say E, we write down all the possible patterns which contain n minus 1 terms, where n is the number of enzyme species. For example, here the enzyme species are 3. So, we will take all patterns that have 2 steps, only 2 steps and nothing else, and those patterns will be considered. And second thing is that only those patterns which end up synthesis of that species, not the patterns that lead to the breakdown or the which go away from that species will be considered. Now, for example, in this case you will notice that you will consider the three patterns that will be applicable. Now, here in the case, because all these steps are reversible, there will be three patterns, and you will notice that you have k minus 1 and k 3, you have k minus 1, k minus 2, and also k 2, k 3. Now, the fraction of this the total enzyme concentration that it will represent will essentially be proportional to the sum of the kappa factors, sum of the products of the kappa factors. That means essentially E upon E naught will be essentially equal to k minus 1 k 3 plus k minus 1 k 2 k minus 1 k minus 2 sorry plus k 2 k 3 divided by the sum total of all the products of the kappa factor. That means all the kappa factors which sum put together for E, Es and Et. I mean the numerator whatever we will write for Es and Et will also be added in the denominator. So, the sigma that will be E0. So, the enzyme concentration, the concentration of the E species will be essentially total will be a fraction which will be given by such a expression.
Just a minute. Will you not consider K3P?
K3
Or sorry, K minus 3P already.
K minus 3P is already considered.
Sir.
Sigma is the sum total of the products of all the kappa factors. For example, we will have the products of kappa factors for E, we will have for Es and also for Et. The total sum will be the sigma on the denominator, because that will represent essentially the E0. Or you can write essentially E will be equal to E0, this you can multiply by E0 and that will give something like that. Now, similarly, you can write for Es, the Es will be given by again three different patterns. This one, here it is your K1S and K minus 2, K minus 2, K minus 3P and K1S and K3. Here also you will notice that the concentration of E will be E naught, K1, K minus 2 into S plus K minus 2, K minus 3 into P plus K1, K3 into S. In the same fashion for Et, we will come out to be, oh sorry, the other way.
So the last is K1, K3.
Pardon?
Last one is
K1, K3. This will be your K minus 3 into P and this will be K2, K1S, K2 and K minus 1, K minus 3 into P, and the fraction of the Et of the total enzyme concentration will be E0 into K2, K minus 3 into P plus K1, K2 into S plus K minus 1, K minus 3 into P. Now, you can write the reaction velocity. The reaction velocity for such a reaction will be given by K3 into Et minus K minus 3 into E into P. The rate expression for that will be this expression. Now, we can substitute the value of the Et and E in the expression and you end up as E naught, and after deleting all the factors which are positive and negative, you come out with the K1, K2, K3 into S minus K minus 1, K minus 2, K minus 3 into P whole upon K minus 1, K minus 2 plus K2, K3 plus K minus 1 K3, sorry, this is not, this is the whole bracket, plus S K1 K minus 2 plus K1 K3 plus K1 K2 plus P K minus 2 K minus 3 plus K2 K minus 3 plus K minus 1 K minus 3. So, this comes out to be the rate expression for such a reaction mechanism. Now, you will notice that if you consider that this had this reaction not been reversible totally, then the term P will become 0. If it was a reversible reaction, you can just put P is equal to 0, that means this term will disappear, this term will disappear, and the rate expression will become for a irreversible reaction step. And so, I mean, these are the steps. Basically, just to summarize, first of all you write the reaction mechanism in a cyclic manner, write all the kappa values at each of the interconversion arrows of the different enzyme species, express the fraction of the concentration of a particular enzyme species of the total enzyme concentration in terms of the product, sum of the product of the kappa factors, and then write the rate expression taking the value of the particular enzyme species from those expressions. So, that is what we do essentially, and one can write rate expression for a complex reaction mechanism.
The denominator here is the sum of the kappa factors.
Denominator is totally all the sum of all the kappa factors, all the 3 species, their kappa factors the sum, and essentially you will notice that because here we have taken all the 3 steps or all the 3 enzyme species, they are convertible reversibly. So, all the patterns are coming into picture, but if you notice into a reaction mechanism that some of the steps or some of the interconversions are irreversible in nature, then many of the patterns will diminish, will disappear, because there will be no chance of synthesizing that particular species through that, but we will only consider only those patterns which will consist of n minus 1 steps. That is, now if we let us say now we with this background, if we take a general sort of a case from a binary substrate reaction, that is particularly for the ordered ternary complex formation. Now, you will recall that the reaction mechanism in this case was expressed E goes to EA, then EA goes to EAB. Minded the reaction, the binding of B from E is not possible in the ordered mechanism. We are considering that only A can bind to free enzyme, and then this essentially goes to E by with the release of the product X, and then this goes to E with the release of the product Y. And let us say this is K1 into this is K1S, K minus 1. I am just writing the kappa values right on the arrow, so that it while writing rate expression it is easier. And this is your K2 into B, K minus 2, this is K3, this is K4. Now, if you notice that, let us say now we look at there are 4 different enzyme species E, EA, EAB and EY. The last 2 steps are irreversible in nature, they only lead to formation of 2 products in a sequential manner. Now, if we write for E, you will notice that there should be 3 different possibilities. One is that the E can be synthesized in this route, that is your K minus 1, K minus 2 and K4. The other is this can also be synthesized in this form K2B, K3 and K4, and also K minus 1, K3, K4. These are the 3 possible patterns which are possible, and so writing for the concentration of E will be your E naught into K minus 1, K minus 2, K4 plus K2 K3 K4 into B plus K minus 1 K3 K4 whole divided by sigma. So, the concentration of E will be given by this factor. The concentration of EA will be your given by here. If you notice that it will be formed only by two patterns, that is your K1A, K minus 2 and K4, and K1A, K3 and K4. These are the only two patterns which will lead to synthesis of EA and none other, because all other patterns there will be no reversible step. And now I think I will again like to remind you that just as a matter of convenience, we consider only those steps which lead to the synthesis of EA. All steps which go outside from the EA are not taken into account. And so, for this the concentration of EA will be given by E naught K1 K minus 2 K4 into A plus K1 K3 K4 into A whole upon sigma. Then your similarly your EAB will have only one pattern possible, because EAB, as you notice, it is emerging only from the E side, from E via E and EA, and it cannot come from EY and E. So, you have only one pattern for EAB, that is your K1A, K2B and K4, and therefore, the EAB will be given by E naught K1 K2 K4 into A into B upon sigma. Similarly, EY will also have only one pattern, K1A, K2B and K3. So, this will be given by E naught K1 K2 K3 A into B upon sigma. So, you have now the relative concentrations or the relative fractions of each of the enzyme species that are present. Now, if you recall, when we talked about in the case of allosteric enzymes, the relative contributions, they can also be arrived from a similar analysis to have the relative concentration of each of the enzyme species. Now, from this then you can write down your rate of reaction as equal to K3 into EAB. You notice that if you look at the original rate expression, the product is being formed. You can have either as K4 into EY or you can have K3 into EAB. Both the reaction rates will be identical, and so you can write as K3 into EAB, and that will give you.
So why will they be identical?
Pardon? No, because we are from the right in the main reaction mechanism we are writing A plus B going to X and Y. We are considering a unimolecular reaction. If they are not unimolecular, then you are right, the rates may be different, but as long as we are assuming that the stoichiometric relationship is unimolecular, they will be identical. And so, if you substitute the value of EA by, you get E naught K1 K3 K2 K4 into A into B whole upon sigma, total sum of all the numerators of earlier species, and if you simplify that just by arithmetic manipulation, you get into an expression like K3 K4 upon K3 plus K4 E0 into A into B whole upon K4 K minus 1 K minus 2 plus K minus 1 K3 whole upon K3 plus K4 K1 K2 plus K4 K minus 2 plus K3 upon K2 K3 plus K4 into A plus K3 K4 upon K1 K3 plus K4 into B plus A into B. Now, this is what we have rearranged it into the format of the general rate expression and in the form of individual rate constant, and you will notice that the term, this term essentially indicates a value of Vm on the numerator. This term essentially is K dash A into Kb. This is your Kb and this is your Ka. Of course, from this again by dividing from this term you can get the value of K dash A. So, essentially this is identical to that what we essentially wrote the generalized rate expression proposed by Alberti, and you one can get the individual rate constant in the form of the 4 parameters that we talked about: Vm, K dash A, K and Kb, which represent the kinetic parameters for a given. Now, you notice that in the case of a Thoroughly chance mechanism, which we considered a special case of the ordered ternary complex formation, and we assume that in the case of Thoroughly chance mechanism the presence of this complex EAB was very the complex EAB was very unstable, as if that the EA directly goes into E by forming a product X and there is no significant concentration of EAB present, which essentially indicates that in the case of Thoroughly chance mechanism your K3 term from the reaction mechanism is much greater than K minus 2. Essentially the essential condition implying the non-existence of the term the insignificant quantities of EAB, essentially directly conversion of EA into E by, although it is via EAB, but the complex EAB is not very stable, essentially means that K3 is much greater than K2, and you substitute those one, you get a reaction expression, rate expression as K3 E naught AB upon K minus 1 K3 upon K1 K2 plus K3 upon K1 into B plus K3 upon K2 into A plus A into B. Again the same pattern of generalized rate expression that we noticed in the case of ternary complex formation. Both the types of ternary complex formation, they follow the same pattern, and essentially you will notice that when we talk about the binary complex formation and the case we talk of ping pong mechanism, the pattern will change, and that is what will clearly indicate the existence of a different mechanism. And also, I mean, basically this is what you can further simplify this to write your K1, multiply this by K1 K2, K1 K2 K3 E naught AB upon K minus 1 K3 plus K2 K3 into B plus K1 K3 into A plus A into B. That is what the final expression for Thoroughly chance mechanism, and therefore one can go into such a mechanism and get the rate expression.
So what is the practical utility of getting this expression?
The practical utility is whenever you want to determine, there are two things. One is to understand the reaction mechanism that a particular reaction follows, and second thing is even for, let us say, design of reactors, you need the kinetic rate expression and the individual rate constants if you want to really design and get the final simulated values or let us simulated profiles for the reactor performance. As I mentioned that there are right in the beginning when we started talking about the significance of the kinetic studies, it basically allows you to understand the reaction mechanism. The getting their individual rate constant, you can also manipulate them in the case of for the design of reactors and for simulation work. And third thing, the information on the individual rate constant will also give you a understanding of how the enzymes they will function at the metabolic level. As I mentioned that, write a simple example of your glycolytic enzymes, that for example when you have hexokinase, now the glucose can enter into more than one metabolic pathway. Now which metabolic pathway it will enter will require the understanding of the reaction mechanism and individual rate constants. Now and also I think it is significant to note that most of the enzymes that are present in the living cells are essentially bisubstrate reaction and not really, although as I mentioned that they can be understood, and by and large very often they have been for the sake of simplicity have been analyzed keeping in view the mechanism in kinetics, but always it may not apply because the concentration of the second substrate will never be excess in the living cell. That will be always a comparable concentration, and therefore it will be always useful to have understanding of the now the other the bisubstrate reaction mechanism was a binary complex formation, and the case which we talked about was ping pong mechanism, which essentially stated that at no stage a ternary complex forms. As soon as a binary complex form, a product is released and the modified enzyme then interacts with the second substrate and the second product is formed. And the reaction mechanism as we expressed earlier is your K1A, K minus 1 EA. Now here at this stage a modified enzyme complex and product X will be released, K2, K3 into B, and you get E dash B, and you again get another product formed by and with the K4 rate mechanism. So you notice that there is only one reversible step here when the first substrate binds to the enzyme, rest of the steps are all irreversible steps. And if you again consider the 4 different enzyme species present here, E, EA dash, E dash and E dash B, you have for E you can write the pattern as K minus 1, K3 B and K4, and similarly you have another pattern K2, K3B and K4, and the rate expression or the not rate expression, but the relative concentration of the enzyme species E will be E naught, K minus 1, K3, K4 into B plus K2, K3, K4 into B upon sigma. Similarly for EA you will get only one pattern which will be feasible, that is your going in the anti-clockwise fashion, that is your K3B, K4 and K1 into A, and the relative concentration will be E naught, K1, K3, K4 into B into A upon sigma. and for E naught, E dash, E prime, you again have only one pattern, that is your K2, K1A and K4, and that will be E4, K1, K2, K4 into A upon sigma, and E dash B will be also only one pattern, K1A, K2, K3B, and you will get E naught, K1, K2, K3 into A into B upon sigma. So, having the relative concentration of each of the enzyme species, then you can always write the rate expression, that is your V as equal to K4 into E dash B. It can be either K4 into E dash B, or it can be K3 into EA. Either of them can be written, and
K2 into EA.
pardon, K2 into EA, right, K2 into EA, or if you write, let us say, or this can be also equal to K2 into EA, and therefore you can again substitute the values and get your reaction velocity expression as your E naught, K1, K2, K3, K4 into A into B whole upon K1, K2, K4 into A plus K3, K4, K minus 1 plus K2 into B plus K1, K3, K2 plus K4 into A into B. Now, this again, if you just try to bring it in the form of a generalized rate expression, you will notice you get as K2, K4 upon K2 plus K4 into E naught into A into B upon K2, K4 upon K3, K2 plus K4 into A plus K4, K minus 1 plus K2 upon K1, K2 plus K4 into B plus A into B. Now, here you notice a significant difference from the generalized rate expression. You have the Vm term, you have the Kb term, you have Ka term, but the K dash A V term is missing, which implies essentially in the case of a ping pong reaction mechanism, the term K dash A is 0, and essentially that makes a very big probably point to discriminate between the different reaction mechanisms. At least you can distinguish whether the enzyme reaction follows a binary mechanism, binary complex mechanism, or a ternary complex mechanism by just evaluating the value of K dash A. You have noticed that earlier when we talked about the analysis of the bi-substrate data based on the double reciprocal plot, and the secondary plots of the slope as well as intercept. For example, in the case of 1 upon A and 1 upon B, if you plot, you get a profile like this with B bearing, with variation B, and if you plot slope versus 1 upon B and similarly intercept versus 1 upon B, you can determine the value of Ka, Kb, K dash and Vm. So, basically by analyzing these parameters, one can distinguish if the magnitude of K dash is 0, one can conclude that the reaction mechanism under study follows a binary reaction mechanism.
But K dash A was interpreted as the dissociation constant of E plus A reversible.
Right.
That step is here in the reaction also.
Right.
It's ping pong mechanism.
No, basically that means that the dissociation of that means breakdown of the EA complex is very slow. 0 means it the magnitude goes to a very small value, it becomes a very stable system. Now, so therefore, if you look at now, if we consider that now the second part of today's lecture, as I mentioned in the beginning, to discriminate between the different reaction mechanism, one of the tools we have got the analysis of the data, the reaction rate data based on double reciprocal plot. We can easily distinguish and get the magnitudes of the values of the various kinetic parameters Bm, Ka, Kb and K dash A, and if the magnitude of Ka dash is negligible or 0, one can conclude that it is a binary reaction mechanism and not ternary. Unfortunately, this analysis will not yield any information about whether it is an ordered or a ternary or a random mechanism, ternary complex formation, because in both cases the rate pattern will be identical. Of course, the magnitude of the Ka, Kb and Ka dash might vary, but they will have a positive value. In those cases, the another factor which we have, which we make use very often for analyzing the reaction mechanism, is that of your the enzyme inhibition data, because if you study the use of one of the product of these bisubstrate reaction as an inhibitor and see their interaction with the effect on the rate expression, you will notice that the different product X or Y, when used as inhibitor, they give rise to different pattern of inhibition that we have noted earlier. That means uncompetitive, non-competitive or a linear mix. The linear mix was a case of non-competitive. And so, if you, I will not go into detail of analysis of those, because they will only have a very long expressions, but if you just consider the summary of the rate expressions, say rate equations, you see that I have just summarized here the random ternary complex formation. It is exactly identical that of our generalized rate expression, ordered ternary complex that we have written today, and Thorel chance mechanism and ping pong mechanism, and the species in the bracket are the ones that lead to that term, actually that correspond to that enzyme species. And now by studying the inhibition pattern of each of the product used as inhibitor, if you consider, let us say, a compulsory ordered ternary complex formation in which the substrate A binds first, if you use the two product Y or X separately as inhibitors in the reaction and notice the effect of Y and X as the nature of the inhibition, in the case of with respect to the bearing A, you get a competitive inhibition pattern, with respect to X as the inhibitor you get a mixed inhibition. So, you get a completely different patterns, and as you will recall that when we were discussing the inhibition patterns, we also mentioned very clearly that a major use of the inhibitory patterns is in the analysis of the bisubstrate reactions to identify their reaction mechanism, and one can derive these expressions and get the different types of inhibition pattern. This is just a summary of the whole thing, that when you take A binding first and use one of the product and out of the two as the inhibitor, you get a different pattern, and with respect to bearing B you get a different pattern. So, by getting the data, inhibition data on the reaction bisubstrate reaction kinetics, either by choosing one product or the other product, one can get a set of data, and from which one can conclude whether it is a ordered ternary complex formation or a random ternary complex formation. And of course, identifying ping pong by Y or the ping pong mechanism is simply by directly from the effect of substrate concentration on the reaction rate itself can lead you to that kind of scenario. And therefore, as you will notice that the combination of the two studies, particularly the effect of substrate concentration and the studying the nature of inhibition with respect to one or more of the products will give you the nature of inhibition pattern, and that information can give you a conclusion about the nature of the reaction mechanism and in the case, and most of the reactions that lead to such kind of inhibitory patterns have been then concluded to follow one or the other ordered or ternary complex mechanism formation. So, I think with this we will be completing our kinetics of enzyme catalyzed reaction. Just to summarize what we have covered so far in the kinetics, we have initially looked at single substrate, single intermediate reactions leading to hyperbolic kinetics, the validity of this kinetic pattern to a whole range of reactions under different conditions. Thirdly, we came to inhibition patterns with respect to the single substrate reactions and the effect on the inhibitor concentration on the reaction rate, also the effect of activators on the reaction rate. Then we came to effect of pH, effect of temperature, and they are used for understanding the reaction thermodynamic parameters and other mechanistic aspect. Then we came to bisubstrate reactions and effect of the substrate concentration, writing the rate expression, and finally concluding with the discrimination of the various reaction mechanisms that are involved in bisubstrate reactions. So, that summarizes, I think,